All right. Well, welcome to chapter 3 of WTF is FFI. I almost said the actual title.
Yes.
That's a big no-no, especially at work.
No.
You cannot do that. Which
Not
is why,
especially not on YouTube.
especially not on YouTube. YouTube is a pristine place full of manners and well-to-do citizens. So don't want to stick out like a sore thumb there. Well, welcome to chapter 3 of WTF, what is FFI, and I'm here with my co-host Aapo. Say hello, Aapo.
Hello. Nice to be here again after a
Yes,
bit of a pause.
a bit of a hiatus, but no
Yeah.
worries there. Everyone is always dying to learn more about FFI, and that's where we come in. Um, and I think we have some exciting updates. Just just about Deno himself. And I think Apo, do you want to say a little bit about your expanded role at Deno?
Uh, Essentially, I've become a part-time contractor for Deno. Nothing major. I'm just, trying to help out a little.
So what he's saying is he's pushing his FFI agenda here at Deno, which is something that we all love. So thank you for your contribution there. So let's get started for this video. If you could just summarize this video in like a 10-second soundbite, what are we going to be covering in this video?
So last time we asked if there would be any libraries, C API libraries that you would want to see adapted to Deno. In the end, there wasn't. So now we're going to see how I actually adapted libclang, the C API for Deno. So we're not going to be reading my code. We're going to be rewriting the stuff that I have done already and seeing how it actually works, what does it do, and why does it do it. But basically, we're looking at a real live example of how Deno FFI can be used with a real live library.
Awesome. People love real life examples, so let's get started. I will add your thing to the stream. Here we go.
Yeah. So this is where we start. Just as usual, we start with the Deno DL open call to open a library. But this time we're not using some library that we have here close to us already. Let's actually delete that one. Instead, I'll be loading the libclang from my user lib directory. Yeah. And the library has already been partially implemented here. So we have a couple of functions: clang get C string, clang dispose C string, because we're good people and we dispose of the resources that we've taken in. And then we have clang get clang version. And just as kind of dissimilar to previous, I'm actually taking out the symbols out of this library and putting them into a constant called libclang. This is just so that we can avoid always writing the symbols everywhere. And then aside from that, just as before, we call functions from this exposed object. We have the clang get clang version here. We call it, and it says it returns a uint8 array. So this is actually returning a C string T. And what is C string T? I've exposed a type def here into its own, or extracted a type def into its own constant. So C string T, this is a type, a structure type from the Clang API. And the C definition essentially says that there is a pointer in it, and then there is a U32 in it. We don't, of course, to us, this object struct means kind of nothing, but it's useful. It's very useful here when we're defining our APIs. We can see immediately that, aha, this parameter here takes a C string or CF string. and here getClang version returns a CX string. So okay, this kind of seems reasonable. And actually, if you've not seen this struct syntax before, this is what has probably been previously discussed. Deno FFI nowadays also supports structs by value. So these C APIs say that they return essentially a buffer of memory. The way that it's done technically in the computer at like CPU level, we don't care. It's just we get a buffer of memory and we own that buffer after we get it. But so we get that buffer of memory here. It's a uint8 array for us. And then we use the getCstring function. This getCstring function says in Clang's API that it gets the C string out of a CX string. And we have the Deno unsafe pointer view API getCstring to turn a C string into a JavaScript string or read a C string from the pointer. And this looks already fine. So let's run it. Deno run unstable allow FFI and session 3. And indeed, we get the Clang version. So we're running Clang 1507
Nice.
on my computer here. Now, we should, of course, be nice and get rid of the stuff that we've allocated. So let's dispose of the C string there as well. But
Yep.
this is again, yeah. Oh, yeah. Go ahead.
No, it's important that it's important to maintain the balance of the force when dealing with low-level stuff like this. You don't want to take too much. You don't want to give too much. Be mindful of your own waste.
Yeah. But of course, this like getting the Clang version, that's not like too useful yet. So what the Clang API is actually used for is parsing C, C++, and Object-C headers and source files. So we would want to do that. Now, I'm not going to bring up the Clang C API definitions here. You can find the index files online, and you can find relatively good documentation about what it means. But the way the Clang C API works is that first we need to create an index before we start parsing some header file or some code file. And for that parsing index creation, we have this function called createIndex. It takes two parameters, which are both integers, and I've added the parameter declarations here so we can actually kind of get some better feedback. They both take 0 or 1. They're essentially just booleans. And it returns a C index T C index in the Clang declarations. The C index T is just a pointer. So I'll just add this pointer definition here. When I was writing the libclang API or Deno FFI bindings, I found that it's just much neater to have these function definitions or variable definitions, even for stuff like pointers, because here I can still see that, this function is returning a CX index, even though at the end it just becomes a pointer result and the information is kind of lost, but it's still better than nothing. So with that, we can now actually create an index. The first parameter was exclude declarations from PCH, whatever that is. Maybe don't do that. It might not be interesting, might be. Display diagnostics. Yeah, we definitely want diagnostics. So let's put 1 for that. And we can then check that there is indeed something written in, or we get some kind of pointer. Now we should, of course, also add dispose index, but we'll leave that out because it's not important right now.
Yeah. So what specifically are those parameters? What does that mean? Exclude decimals from PCH.
exclude declarations from PCH. PCH had something to do with the. No, I can't remember. I've not really used these. They're just there.
Okay.
Yep. So now that we have an index, from an index or in an index, we can start parsing header files with it and code source files. Now, I don't have a source file here ready, but we could just go to last week or last session, and we have here our good old libcpp, which created our lovely prime secret class and so on. This horrible mess of a not RSA library. We'll parse this. We'll see later why this is actually kind of a bad idea, but bad ideas lead to innovation, so we'll go with that. And since this is not a header file, but a source file, libclang has a separate API for this case. Again, I'm just copy-pasting from other places, but don't mind that. We have this API called createTranslationUnitFromSourceFile. So that's for code source file. And it returns a CX translation unit, which again is actually just a pointer. So I'll add that here as well, the definition. The parameters it takes is first the index. You can kind of think that this is the this parameter in JavaScript. Mm-hmm. Then there's a C string. So I've already have included these built-ins here. So C string is just a buffer, which contains a encoded UTF-8 string. Then there's an integer here, a C string array, and a uint, and finally a buffer of CX unsaved files. We'll not care about these, so we can kind of forget those. The actual parameters are first the index, then there's the source file name, so which file are we actually parsing. Then there's a number of clang command line arguments, and the command line arguments themselves as a C string array, or an array of pointers, essentially. And then we have the number of unsaved files and the unsaved files themselves. Now, how do we use this API? First, okay, we need to give the index. Sure. Then we would need the source file name. For us, that would be the session2/libcpp. All right, but of course, this is just a JavaScript string. We can't do that. So we need to encode that to actually get a C string. So we could do this, but now this is again an invalid C string because C strings must end with a null pointer, null byte. So we could add that, and now we would have a proper C string. But this is all a bit of a handful. So I have already prepared a helper function C string here, which does exactly that. It encodes a string with a null byte at the end. The next parameter was the number of clang command line arguments. Now, clang command line arguments is a bit of a hairier thing. If you've never done any Clang or GCC compiling, then you can maybe shut your ears. But if you have, then when normally you would write just Clang and then maybe X C++, so we're compiling C++, and maybe we use some include file like user lib whatever. These are the command line arguments, and we need to give the exact same ones that we would use normally on the command line. In this case, we're going to give 2 arguments. So the first argument will tell that we're compiling or parsing C++, and the second will indeed be an include directory. And the way we create these command line arguments, we need to give a C string array. So that's an array of pointers, and the length of it is defined by this previous parameter. We could take each of our command line arguments that we want to give, like C++ and iuser lib, whatever the path is. Oops, let's make that parse. We could do this and then run through this, making a C string out of each, then getting the pointers out of that, and finally creating another buffer that contains those pointer values. But again, that's a bit of a handful. So I already have a helper function or helper class that will do this for us. It's as easy as that. Lovely.
Can we see the helper function just really quickly to see what it looks like?
Yeah.
Oh, wow.
So basically, we go through the strings, we count their lengths and add a null byte for each. Then we finally, this is extending a uint8 array, so we create the uint8 array finally with the number of strings times 8. So that's the memory for the pointers, and then how many characters we have in the strings. Then we start encoding into this buffer. We encode each of our strings into the buffer, and we put the pointer value into this buffer.
Yeah.
Wow. Basic, simple stuff. In some ways, there are very good reasons to not do any of this in JavaScript, but also there's good reasons to do this in JavaScript. This is, like, at least on a theoretical level, this is the most efficient way, I believe, to do this. There is no kind of better way, or okay, maybe I should stop lying.
Hear that, everyone? That is a challenge from Aapo. He thinks that is the most efficient way. If you can find a better way, please comment below. I'll be reading the comments.
Okay. In my case, the include path was this. User lib clang 1507 include has headers that we need for this parsing, because our C++ file itself is using headers. Yeah. So that was the fourth parameter, and then we had the number of unsaved files, which we do not care about. There's not going to be any unsaved files here, and also the unsaved files themselves, we don't care about that. So I'll just give a null buffer. This is an empty uint8 array I've prepared here beforehand. Oh. So this should now work, I'm hoping. I'll just take the return value and name it TU, and let's see if we get some valid value out of this. We indeed do. Hooray.
Wow. Nice.
So we can actually even see how quick is it to parse this. Apparently, it took about 216 milliseconds to parse our header. So we can be reasonably certain that it's actually doing some work. This is not just a no-op call. Yeah. But, of course, having just a parsed translation unit doesn't give us anything. We still would want to see, like, what did you actually parse? What is in the file? And for that, we need cursors. For the Clang API, a cursor is a class that you can use to go walk through the headers or the source files that it has parsed. And cursors have a ton of APIs available. We're only going to check out a very, very few ones. First, let's bring in some definitions. So we have this function here called getTranslationUnitCursor. So this will take a translation unit and give kind of a top level cursor, which can then be used to actually start traversing down. But we also need to, of course, define what is this cursor. And it is a doozy. Let's put it here. Where do I have my CX cursor? There I have it. Yes. The CX cursor is a struct. It's 32 bytes in size. It first has the cursor kind in it, then it has some data and some pointers. We're not really interested in what's in it, but fun to know. But of course, we need to tell Deno FFI that this is what is in the buffer, so it can actually calculate how big of a memory it should reserve and so on. So, okay, now we can get a translation unit cursor, and we can also, using this get cursor kind, we can get its kind. We'll look a bit later at what that actually means, but let's first actually get that cursor. So again, we go to the libclang API, and we get the translation unit cursor from this translation unit of ours. We can log it from cur. And then let's also console log its cursor kind. Seems like we got something.
Yeah.
So we indeed get a uint8 array of 32 bits, 32 bytes, sorry. So that seems correct. We agree with what Deno is saying. Deno is allocating, and then the cursor kind gives us a number 350. Now, I could explain to you what, or go through the CX cursor kinds, but luckily I already prepared it here, and I don't have to write this again because this is quite a few lines. This is the full definition of the CX cursor kinds, and if we look here at 350, we find that it's CX cursor kind, CX cursor translation unit, cursor that represents the translation unit itself. So this looks correct. We got the translation unit cursor, and it says that its kind is translation unit cursor. So, okay, this looks fine.
So out of all the cursor kinds, are those just types of cursors that could
just types of cursors? Yeah.
Wow, how many are there? Like hundreds, it seems.
Hundreds, yeah. Last defined number is 700, but of course there are gaps here, like 604 is last before 700.
Okay, interesting.
It's quite a few, but we'll just leave it there and decide that, okay, we can actually say that this cursor kind, let's say that this is CX cursor kind. So now we can actually see that if kind equals CX cursor kind and translation unit length. Works. So we can kind of tell Deno that, hey, this number that you're returning here, that's actually going to be one of these enum values, and then we can compare it there. But okay, so we can get the translation unit cursor itself, but then we would want to actually get somewhere from that translation unit cursor. And the way we do that in the Clang API is through visitors. So last time we took a bit of a look at callbacks. We were creating Deno FFI callbacks and calling them from various threads and running into various fun segfaults. This time, I think there won't be any segfaults, but we need to work with functions or callbacks again. So I have already a built-in function here called func, which just takes any callback definition and returns the parameter name function. And then this visitChildren Clang API is such an API that it takes a cursor, it takes some client data. This is just essentially a pointer to whatever you want. And then it takes a callback function. And it will then walk through all the children of this particular cursor that you gave it, and will call the callback with each cursor and that cursor's parent and the client data that you originally gave, but we don't actually care about that too much. Now, the definition of the callback is something like, where do I need to put it here, something like this. It's given cursor and parent, and then the client data, and it returns, or a CX visit result is needed to be returned from it.
So here the parent-child relationship is in cursors, and how exactly does that work? Is it like the cursor is pointing to a part of like the next part of the file or something?
Yeah, we'll see it quite soon, but basically when we start from the translation unit, its children will be the kind of top level items that have been defined in your C++ program. I'm no big expert in C++, but as far as I understand it, when you include a file, it's pretty much the same as just copy pasting the source of that file where you included it. Of course, there's if-defs to make sure that you don't copy paste multiple times. But so in that sense, when we're talking of a translation unit cursor, it's at the very top of the file before any includes. Then when you ask for its children, it will take the first item on that whole file and it will give that cursor as its child, and that child's parent will be the translation unit cursor again. And then it starts, as you go along with the children, it starts stepping down through all the children in the file. And funnily enough, through that, actually your code will probably be the last items that it steps through, because all the includes will be at the top.
Got it. Yeah. Interesting. Okay.
Yep. So we have our cursor. We've defined the callback or the API for the callback. Now we need to actually create a callback for it. And I'm just going to not even be shy of just copy pasting because we're going to do some partially interesting stuff here. I need to actually copy some more definitions. The actual enum for the visitor result, I forgot to take that with us. Let's put it here with the visitor result type definition. This is actually why I have the T at the end of all type definitions, so that they don't overlap with the actual definitions for TypeScript. So, all right. I define this let variable, so a mutable variable visitor callback, which just takes a cursor and a parent cursor and it returns CX child visit result. The default action here is just to throw an error because this is not correct. And then I create a Deno unsafe callback that takes the actual 3 parameters from this callback definition. So that's the cursor, the parent cursor, and then the user data. We do not care about the user data, so we let it be. And now we just call this visitor callback that we defined here. Now, obviously, if we ran this function right now, somehow, then it would call this invalid callback and throw an error. We don't want that. So instead, we define our first kind of, not a method, but our first like proper JavaScript side API. We create a visitChildren function. And this actually takes a cursor and then it takes a JavaScript callback with the type of this visitor callback. And it returns some number. We don't care about that too much. And what it does is first we take the previous visitor callback. We put it in a safe place here. We replace the visitor callback here, or visitor CB mutable variable, with our received callback. Then we finally call the Clang's visitChildren callback, or visitChildren API, sorry, with our visitor CB pointer here and the cursor that we were given. And then we just give 0 as the user data because we don't care about the user data. The visitChildren function is synchronous. It will keep calling back to us with this visitor callback as many times as there are children, and it will not return until that iteration has completed. So we can kind of safely say that we won't reach this next line until the visitor callback will no longer be called, at which point we can return the previous callback that we'd saved off, return it to here, to the variable, and then we can just return the result that we got from this visitChildren function. Now with this, we can finally start actually visiting our children. We have the cursor somewhere here. It's still the translation unit cursor. And now we just give a JavaScript function. We'll get some child cursor here. And then there's a parent cursor as well that we're getting. And we'll need to return a number here. Let's keep that in mind. And we can start doing something with these children that we get. Let's, for instance, call childkind, and then we have the libclang API to get the cursor kind from the cursor. We can do that, and then we'll return where it's needed to be, of course, the CX child visit result. So we'll just call return the continue value. So this will just tell clang to keep calling the callback with more children. And now if we run this, we get a whole lot of stuff. It's more than my terminal will actually remember. If we take a look at these.
So those kinds are the type the cursor types, basically.
Cursor types, yeah, cursor kinds. And if we can, for instance, check, the cursor kind is what we now want. Does this work? This, of course, doesn't work. We'll need to go to the cursor kind here. Let's look at what 501, for instance, is. It's the macro definition, and then 502 is macro expansion. We're getting a whole lot of macro definitions and macro expansions here. We probably don't care about those. Let's just skip those. So we say that if, let's take the kind here. Child kind is if the child kind is cursor kind and macro definition or macro expansion, then we'll just early return with our continue value. Now when we run this, we should get a whole lot less of our console log spam. Still quite a bit though. There's 503 as well. That was macro instantiation. Let's at least get rid of that as well. There we go. Maybe this will give us, well, there's still a lot, but maybe not too much. Okay. So we can walk through the children and see their kinds, but even if we look at these, like child kind 22, for instance, what is child kind 22? It's a namespace. Okay, that's helpful. Namespaces are what we're probably interested in. For instance, here in our libcpp, which we are parsing, we have a namespace lib, and everything actually we have in this file is inside this namespace. So we would really actually want to, like, we're not interested in this main level stuff. We're actually interested in the stuff inside this namespace. So, whoops, where am I going? There. So we could, of course, here say, like, hey, if the child kind is this to make things a lot easier. If it's actually a
namespace.
Yeah, namespace. Thank you. What's that? Ooh.
Oh yeah, that is the real 503, right?
Yeah. I was wondering why we were still getting 503s in the log. Yeah. So, okay. I could do here, okay, if we have a namespace, then let's do something else. But this is actually still going to be hit upon quite often. And I don't know which is which. So I need some API to actually get information on the namespace itself, or somehow on the cursor beyond just the cursor itself or its kind. And for that, there is a get cursor spelling function. So this takes a cursor and it returns a CX string, which is precisely why we were looking at CX strings in the beginning. Now I can do here spelling equals libclang and get cursor spelling. So we'll take the child cursor here, and I actually have this nice function cx string to string that I'm going to use here. We can apparently I haven't actually annotated or commented this, but this cx string to string will take a cx string, extract or create a JavaScript string out of it, and then it disposes of the cx string immediately. So it's a nice function to work with. It does a lot of the stuff that we want automatically. So using that, we can get our spelling out of this cursor. And now if we log here namespace, let's get rid of the child kind logging because that's a bit much. Oops. Ah, yes, I had forgotten. I need to first do some providing. This is just some stuff that I need to do because this is not fully kitted out. So now we can actually see the namespaces that we're working with here. There's a lot of std namespace and then GNU CXX namespace, GNU debug. Yeah, we're not really interested in any of those. But finally, at the end, we see the one that we want, lib. This is our namespace in the libcpp. So we can do, of course, an if on it. If the spelling is lib, then let's do something fun with it. Now the visitChildren API has this functionality where we could actually return the command to recurse. And it does then start recursing into that stuff. So we could log here. Let's log the cursor kind again, the child kind. And we'll see that there are still a lot of namespaces, 22s, but then there's 9, 5, 4, 1. 9 is a variable declaration. 5 is an enum declaration, 4 is a class declaration, and then 1 that's just the end. If we look at our code here, actually, we can see that we have here a variable, then we have an enum, then we have a class. So that's definitely our code there.
Yep. So it seems like
enum class.
Right, so passing the recurse, you're like going into the namespace.
Yeah.
Yeah, that's cool.
So this is for like, if you were writing C, this would be a godsend because now you can actually like do stuff. But actually in JavaScript sense, this is pretty meh. The reason being that like here, we don't actually want to console log when we're not recursing yet. And if we're already recursing, then we probably want to do something more than just console log. So we would need to have some kind of like is recursing Boolean here or something, but that's just a pain. Instead, we can just call the visitChildren function again. Let's call that CX. And now our visitChildren function implementation, it saves the previous visitor function or visitor callback, replaces with our own, calls this, and this is all synchronous. And once it's done, it returns the previous one to the visitor. So actually, because we did this visitChildren function in this way, it's actually safe for us to call this recursively. And then we don't need any booleans here at the main level or anything, because this callback itself, this essentially a lambda, it already contains the information that, hey, we are now recursing. So here we can actually say, here we can start actually doing some proper kind logging. And let's actually add a one more function here into our definitions. This is a function that Clang says only used for debugging, but you know, live coding is pretty much debugging. We have here get cursor kind spelling. It takes a cursor kind and then it returns a string. So this just takes the kind we get from get cursor kind, and then it returns a CX string that we can log as a nice JavaScript string to see like what is it instead of just seeing 22. So I'll use that with, again, the CX string to string. Let's use that. And now we need to get the kind of this function, this cursor. So get cursor kind, and the cursor was named here CX. So this will give us now the kind spelling here. And I guess we also want to see the naming or the spelling of the actual item that our cursor is pointing to. So we'll do that as well. So that was get cursor spelling and then CX. Yep. And since we're already recursing here into the code that we're actually interested in, here we could just maybe return recurse all the time. So as long as there's code of ours being run or being gone through, then just let's recurse. And now we can actually see some fairly interesting stuff here. Let's see how much of interesting stuff we do. Yeah, here. So we first see that, okay, there's a var declaration. The name is E, apparently. Now, this Clang API does offer us ways to get like the type of this variable and so on. But it also does apparently include it here. So the next is a type ref. So to uint64t, unexposed expression, integer literal. Yeah, okay. Then there's the enum declaration, and its spelling is prime secret validity. And that's obviously our prime secret validity here. Then there's enum constants, integer literal. So it's giving us bit by bit everything we have here. Enum constant unknown, that's this one. Then there's unexposed expression is, I guess, the equal sign here. Integer literal 0, and maybe integer literal comma as well. No idea about that. Then we have the valid and so on. And eventually we get to class declaration, access specifiers, constructor, parameters for the constructor, member list, so on and so forth. So with these already, it would be possible to actually mostly recreate the code that we're iterating through.
Yeah, that's really cool.
Of course, the kind of end goal of all projects like this would be to read our own code or read our own declaration and create our own headers or our own bindings from that. So the libclang API or libclang Deno bindings that I've actually written, those include as part of the build script a use case where the Deno bindings are used to write the Deno bindings themselves.
Oh, interesting.
Complete with actually all the comments and so on.
That's very cool. That's a pretty cool application of something like this.
Yeah. That's actually as far as I had planned for today.
Cool. Yeah, no, this is awesome. So basically, this is like is there a way to just basically like if you were to read a file, you still have to do your own sort of tokenization and create your own kind of AST. But
Yeah.
this way is kind of just like doing that on the C level, from which you could, like you said, create your own bindings and things like that. So
yeah. So this indeed, you have the possibility to use one of the foremost compilers and like tokenizer parsing libraries that there exists without having to implement everything by yourself once again. So this is one place where FFI really shines. Of course, there's quite a bit of code that needs to be written to actually get the bindings, but at some point it becomes pretty automatic to write them. For instance, with libclang Deno bindings, you can just analyze some code with using the bindings and generate more or less automatically bindings from that.
Yeah, that makes sense. So in terms of, and just speaking practically, like real world use cases, like you mentioned that you are doing this with Deno. How are you using that specifically to solve your problems?
So of course, I said the libclang bindings themselves implement or write themselves. We can actually, I'll do the unforgivable and bring in my own code. But if we look at the basic Clang bindings or Clang C API, it's a bunch of header files, and then using the Clang API or Clang bindings, I rewrite those into just Deno FFI bindings, and I kind of keep the same structure that there was originally. So here at the very top we have virtual file overlay create, and then in the generated bindings, well, it's still at the top there as well. So this is just automatically created stuff. Then, of course, the point isn't to just create yourself from using yourself. At work, I have a large C++ library that I'm quite interested in writing an API for. So that's kind of something that libclang Deno bindings were pretty much written for. In a big project, there is too much header files to write the bindings manually. It must be done automatically somehow. And in my case, there is no better source of data. There is, for instance, no JSON format documentation or anything that I could parse with Deno. I need to parse the header files. So, okay, Clang can do that for me.
Yep, that makes sense. Yeah, that's a really good use case for something like this. Awesome, very cool. Well, I think this is such a really great walkthrough with a real world example. And to our viewers, if you have any questions, leave them in the comments. If you have anything that you want us to cover in a future episode, let us know in the comments as well. And yeah, any final thoughts, Aapo?
keep making good seg faults and send them over to me.
Yes, Aapo is collecting seg faults. That's right, you heard him. Any good seg faults, send it over. Add it to the comments or in our Discord, and yeah, we will talk about that in a future episode, maybe. Who knows?
Yeah.
All right. Well, thank you so much. Thanks for watching, and yeah, we'll talk to you soon.
Thank you.